Today's lecture is part 2 of our lecture on the ROC properties when we are doing the Z transform. In today's lecture, we will focus on the ROC of special Z transform, which we call rational functions, and we will work out an example on the Z transform of rational functions. So we say a function is rational if it can be written as the ratio or a fraction of two polynomials. For instance, I'm going to give you an example here. So let's take x of z equal z divided by z minus 1, or x of z equal to z squared minus z plus 1 divided by z cubed plus 2z, for instance. So, or you can write it as a factor. You can factorize the numerator and the denominator. So you can write x of z, for instance, as z minus 1 times z minus 3 divided by z minus, or z plus 10 square, z minus 1. And maybe you can add here a constant, 1/2, let's say. So this is basically what we mean by a rational function. So the most general form is given here. So it should look like this. And you can see here that the AI's are the zeros of the function and the BI's are the poles. And C0 here is just a constant. It's not that important, but you know, if it's there, it is there. So the interesting about rational function is that they occur a lot in engineering applications. And we're going to learn a few easy rules that allow us to basically immediately determine the ROC based on the poles for these functions. But before I move on, let me give you an example of a function that is not a rational function, basically. So if you take this, so for instance, x of z, let's say it's equal to log 1 plus z. That's not a rational function, or x of z e to the z. So any function that cannot be written as a fraction of polynomials is not a rational function. So in terms of understanding the ROC of a rational function, let us first talk about maybe the first problematic case, which is what happens when z goes to infinity. So if we take our previous examples, let's work out this example, x of z equal to z divided by z minus a. And we know that when z goes to infinity, this is going to converge to 1, right? If you had here 2z minus a, it would converge to 1/2. This means that infinity is in the ROC, right? Because the limit does exist. If you take the following, another example, x of z, let's say, is equal to z minus 1 divided by z minus 2 divided by z minus 3. Let's suppose this is, and let's say 2 here, a constant, just to make it a general, look like a general example. So here, if you take the limit when z goes to infinity, right, you're going to have the constant 2 here, and z minus 1 is going to converge to z, and z minus 2 is going to go to infinity like z also, and z minus 3 is going to go to infinity like z. So you're going to have, this is equal to 2z, and this is going to go to infinity. So here, the infinity is not in the ROC. So what really matters is the degree of the numerator compared to the degree of the numerator. If the degree of the numerator is equal or less than the degree of the denominator, like here, then the ROC will be in infinity will be in the ROC. So if you have another case, could be like this. So let's take x of z, and let's take it to be equal to z cubed minus 2z plus 1 divided by z4 plus 3z, let's suppose. So you can see here that the degree of the numerator is 3 and the degree of the denominator is 4. So this is going to converge when z goes to infinity, because when z goes to infinity, this is going to converge, act like z cubed, because you pick the highest degrees, divided by z4, which is 1 over z, which goes to 0. Whereas if I had here z5, then this is going to converge to z5 by z4, which goes to infinity. So this is the second case where infinity is not in the ROC. So infinity is a pole. So this is basically what this property says. It says that if x of z is irrational, so here there is a typo, let me fix it. So this is rational. Then x of z is either has a pole at infinity or the ROC contains infinity, and it's easy to check. All you have to do is just do the limit, and maybe an easier way to check is to check the degree of the numerator versus the degree of the denominator. So if the numerator has a higher degree, then so we have a pole at infinity because the limit does not converge. So this gives you a first easy rule to check whether whether infinity is in the ROC or not. So you just check the degree of the numerator compared to the numerator. Now we're going to talk about property 8, which is a very important property, which is going to make finding the ROC of a rational function super easy. And like I said, in most engineering systems, what we're going to deal with is rational functions, because basically these are the functions that will arise when we're studying a linear time invariant system or an LTI system. Now, in this case, the first case we're going to attack is the case where the signal is right-sided. So this is why this is very important. So this property is true if the signal is right-sided and rational. Then to find the ROC, all you have to do is plot the poles. So like I do here in the figure. So plot the z plot, and on the z plot, just write down the poles. And then this property says that the ROC is going to be the exterior of the largest pole, the circle that contains the largest pole. So as you can see in the figure here. So let me give an example. The idea is simple, but I'll give an example just to make sure we're all on the same page. So let's suppose x of z is equal to z minus 1 times z divided by z minus 2 and z minus, let's say, plus 3. So we know here that on the z plots, we have two poles. We have a plus 2 pole, and we have a negative 3 pole. And now we know that the largest pole, largest in magnitude, is going to be 3, or negative 3. So we know that, therefore, by this property, and given that the signal is right-sided, so I tell you that the signal is right-sided and it has the following x of z. So let me write down here just to make sure, because this is important. And x of n is right-sided. Then in this case, you know that the ROC is going to be the exterior of this circle. Property 9 is about the other case when the signal is left-sided. So this is really important. So the signal is left-sided and x of z is rational. Then in this case, we do the same thing. We have our z plot and we plot all the poles, and the ROC is going to be the interior of the circle going through the pole that has the smallest non-zero magnitude. So you can see in the figure here, so you plot all the poles, and you can see that this pole is the one that has the smallest non-zero magnitude, and the ROC is going to be the interior of this pole. So let us take a simple example here. So like the previous example, so let's take x of z equal to, let's say, z times z minus 1 divided by z plus 3 and z minus 2, and the signal is left-sided. Then I know in the z plot here, I have two poles, one at 2 and one at negative 3. And then I know because the signal is left-sided that the ROC is going to be the interior. Sorry, this is wrong what I did here. So it's going to be the interior of the smallest circle. So it's going to be the interior of the circle at 2. So it's basically here. So it's going to be this part here. So this is the ROC here. Now let's take another example. So let's suppose x of z is 1 over z minus 1, z minus 2. Then here you can see that you have 3 poles, one at 0 and one at 1 and one at 2. So the pole of the smallest magnitude is 0, but you don't count it. So that's what property 9 is saying. So you pick the pole with the smallest magnitude that is non-zero. And since the signal is left-sided, so it's going to be the interior of this circle. Let us do one more example before we conclude this lecture. So the question is the following: what are the different possible ROC for this x of z? So here, instead of telling you that the signal is right-sided or left-sided or double-sided, I want you to analyze for the different possibilities, what could the ROC be? And here, the first thing you need to do is to find the poles. And we can see that we have a pole at 1/3. So the first pole is at 1 minus 1/3 z minus 1 equal to 0. And this will give you that z equal to 1/3. And this is why sometimes you see that we write the z transform as a function of z to the power minus 1, because now you can easily detect the poles. So this is the first pole, and the second pole is 2. So we have 2 poles at 1/3 and at 2. So this is the z plot, the pole 0 plot. So this is 1/3 here, and this is 2. So basically, this is what this slide's saying, is that we have on the pole 0 diagram, we have 2 poles, one at 1/3 and one at 2. Now the analysis is easy because all we have to discuss is the nature of the signal and then the implication on the ROC. So if the signal is right-sided, so here I'm going to color the ROC in yellow, that we know that the ROC is going to be the exterior of the circle going through the pole 2, because it is the pole that has the largest magnitude. So this would be the ROC here. Right, and mathematically it's the region of the plane characterized by this equation. So, and if the signal is left-sided, so here in red, then we have to pick the smallest non-zero pole. So the ROC is going to be the interior of this circle going through the smallest pole, which is z equal to 1/3. And if the signal is two-sided, in green, then it's going to be the ring between these two circles, which what we learned from properties before. So this is the ROC. So depending on the nature of the signal, whether it's left-sided, right-sided, or two-sided, we can determine the ROC if x of z is a rational function. Also, something I forgot to mention is that in the first case, when the signal is right-sided, if you find the limit of x of z when z goes to infinity, meaning z to the power minus 1 goes to 0, you can see that this limit exists, and for this reason, infinity is in the ROC. So here, this includes plus infinity. I want to end this lecture with a do-it-yourself problem. And the question in this problem is the following: is to find the ROC of the following signal with the following z transform, and to find its ROC in the case whether it is right-sided signal or it is a left-sided signal. And here there is a typo. Let me erase this. So here there shouldn't be anything that is z greater than 1/3. So that's the problem here. So find the possible ROC of this Z transform, whether it corresponds to a right-sided signal or a left-sided signal.